All right. It's 2:14 a.m. and you are on call. The first alert hits your phone, and then another, and then 50 more. You don't know if it is one issue or 1,000 more. That's the reality of hyperscale environments. And today, me, Pooja Gupte, will be talking about alert fatigue and some learnings from signal tuning for helping the operations. One real alert surrounded by 99 noisy ones. Alert fatigue isn't just annoyance, it is dangerous. The more noise we see, the slower we react to real problems. And in hyperscale networks, minutes matter. A single hyperscale cloud likely operates on the order of millions of physical network devices. And physical network failures spans layers: server-to-ToR, ToR-to-fabric, and packet loss about ToR. Each layer generates signals, often about the same issue, creating a storm of redundant alerts. Servers might show NIC failure, OS driver cache, server-to-ToR link flaps. ToRs might complain about port failure, misconfigured VLAN. Spine or the fabric layer might show link congestion, and resource hub might complain about telemetry lags and so on. Imagine a hyperscale data center humming along. Dashboards are green, everything is calm. Suddenly, a link failure at a ToR occurs. Maybe it's a faulty optic or a bad cable. In theory, this should be a contained problem. But at scale, nothing stays small for long. Within seconds, servers under that ToR start reporting drop packets. The ToR itself signals link flaps. T1 and T2 switches above it detect rerouting events, triggering path changes. Every monitoring system reacts. Packet loss detectors, application health probes, latency trackers. Suddenly, thousands of alerts are firing. Engineers scramble, teams chase different leads, apps blame storage, storage blames networking. Every minute that passes increases operator stress. Eventually, the real cause, the single ToR port failure, is discovered. But it took hours of triage. Bringing forward the shift. Developing observability around these metrics. Time to detect. The time from when the event started to the event creation time. Time to mitigate, the time it took for remediating this issue, and the time to notify. Time it took to notify the customers about the impact of this event. Observability depends on telemetry. So, to shift our focus on this metrics-driven solution, let's take a look at the open telemetry flow. OCP hardware emitting telemetry, which we feed into the correlation engine, and further into the AI agentic solutions to build the solution. Take a look at this data frame from August 21st for the series of alerts. Which one of them should I have acted on first? The true root cause here was ToR link flap at 10:14 a.m. Before that, I saw symptom alerts starting at 10. So I decided to immediately tag this issue as a root cause and develop monitors around it. Hence, finding faster will help us resolve faster. But the more monitors we create, the more alert fatigue it can cause. Also, you might say, Pooja, what about the symptom alerts? Do we blatantly ignore them? So let's take a look at how we can take it a step further, because we do not want the symptom alerts to get lost in the darkness. Let's leverage them by logically grouping the networking components for intelligently aggregated alerts. The first case over here is device-level aggregation, where you can combine several link-level issues and aggregate them to report the device that is under the problem. You can observe for a rolling window of 2 to 5 minutes up to a certain threshold, and then report for the device under the issue. This is the first case here. The second case over here is span level aggregation. The higher time window over here is because of the longer these issues need to persist. These are the two different correlation techniques. However, taking a deeper look at the patterns of the historical issues, more similar ways can unfold for reducing the noise. Because detection is only half the story, once we know the root cause, mitigation actions can happen faster. Here are some common use cases for which we can use AI to expedite the remediation or the mitigation of the issues. Actions such as opening repair cases with manufacturers, running commands, enriching tickets with actionable insights can be automated using Agentic solution. Here is an example of an Agentic workflow that we recently experimented for running troubleshooting actions on devices. The components here you see is the database on which we set up an event to get triggered, which calls the Agentic workflow. The phases over here are planning, the use of the tools, and the reflection. If the action is not as desired, then you go back to the planning phase and so on. And once you reach the desired result, you store it back into the database. This is one of the experimentations we did, and we observed 90% improvement in the operational efficiency, and more experiments are underway. So bringing forward some open source tools that we can use to automate safely executing predefined steps on devices. Tools such as Ansible, AWS, StackStorm, and LangChain could be used to configure predefined executing troubleshooting steps. The next use case over here is for enriching actionable insights into the tickets. Open telemetry with Grafana, Tempo, Loki for collecting the traces to enrich the incidents. Elasticsearch in combination with the LLM agent to run the queries and summarize them into the text. And Haystack with Llama Index is also a solution. So the last metric I want to talk about is time to notify. The idea here is to have a customer-tenant mapping for resources in the network with a low latency pipeline so that customer tenants can be pulled in the event of a high blast impact and be communicated faster. Reducing alert fatigue while tracking and aiming to reduce these metrics can help restore customer trust. Because customer trust is at the end that matters when you are running a hyperscale environment. So let's detect faster, mitigate faster while using agentic solutions. Well, why not use AI for AI, right? And restore customer trust. Thank you.
All right. Thank you for that. Questions? Please line up. Thanks.
Is there a reason why you're waiting to notify after you fixed it?
No, I mean, I cannot share all the details at what point we notify, but we don't wait. Yeah.
So you talked about taking action, reflect on the result, and iterate, right, until the result is okay and the response is complete. Do you do that in a sandbox environment, simulated environment, or do you do that actually in the network itself, or whatever you're trying to remediate? Because you could actually, as you're experimenting with the plan, you could cause more problems than you started with, right? It depends on what the plan is. So is there a human checking that, the plan, before it gets executed? That's number one. And number two, what is the effect of that iteration? In what environment you would do that?
By effect, what are you referring to?
So I think when you showed the diagram, right? So there is detection of the problem, there is devising a plan, then executing the plan, observing the result, right? And then you ask, is the result okay? If yes, you set the response complete. If not, you go back through the loop. You iterate the plan. So the question, that iteration, as you do that, how do you measure the effect of the plan? Is it run on the live network, or let's say network, on the live network? Or are you doing in a shadow environment or a digital twin environment, whatever we want to label it?
So we, while we are developing the agentic workflow, right, we do that on a test environment, and we observe the efficiency of the workflow, and based on that, obviously there is a human in the loop, as you can see if it's a test environment, right, to correct the inefficiencies if observed.
I see.
Yeah.
All right, and in the plan, is there a review of the plan by humans before? Or
yeah, obviously, yes.
There is. Okay,
Yeah,
so there is human in the loop to review,
yes,
and then execute, and then judge the results and iterate.
correct, yeah.
And then you roll out in production.
Right.
After that. So it's not all done in production through that cycle.
No.
Okay, cool. Thanks.
All right. Any other questions?
Thank you for your great presentation. One question, actually, in reality, we don't have such ideal cooling environment, but anyhow, every time some are observed in the real network, I believe. So it can be the noise to find the actual root cause or trigger of the bunch of the alarms. How do you think? What do you think about screening such a noise to detect such a root cause?
In the cooling environment? Did I got it correct?
No. I mean, in clean environment, it's quite easy to find such a root cause as the first alarm, I believe. But in reality, we don't have such clean environment, but we have the various alarms that exist, I believe. In such a case, then how we can find such a root cause very faster?
Yeah, I think one resource I would refer to is the open config standards developed by Sonic, where they recently shared about the logical grouping of faults with the main fault and sub faults that can be symptom alerts, like the thing that I referred to, right? So you can refer to that as a resource to understand how this logical grouping operates. But I understand what you're talking about. It's a pain because it takes a community knowledge to understand how the grouping would work, and some classification based on, again, community knowledge. But it does require some observation of historical data and some open solutions like open config and what Sonic is working on.
Thank you.
Yeah, sure.
Thank you, Pooja. I appreciate the talk. Thanks for the questions.